Hey guys, thanks for joining me. Today we're going to be doing a review for Exam 3, which is on Tuesday at 7. So go ahead and if you have any requests for any problems you would like us to do, go ahead and leave them in the chat room. What I did is I made a link to the chat in the description, so go ahead and look in the description. You'll get a link to the chat room. You can sign in as a guest and ask questions there. Okay. So this is over essentially everything starting with magnetic fields. That's what it's focusing on. And basically that's going to be things like the force on a current carrying wire, the force on a charge moving with some velocity v, things like Ampere's principle, Ampere's law, and then also Faraday's law. And also what this whole idea of inductance, self-inductance, inductance through an inductor, things like that. So that's basically the material you'll be tested on. All right. So let's go ahead and get started. I already have some requests in the chat room. That's a good place to leave them. So go ahead and start leaving your requests there. Looks like first up is Exam 2011, number 2, Part B. And we also have a request for 2008, number 1. All right, so let's first look at this 2011 two-part B. I'm going to bring it up on the screen here. All right, so let me open it. There we go, and let me go ahead and pop it up on the screen real quick. And so this looks like a question with a current carrying a wire. It's a loop in this case, and let's go ahead and make it a little bigger. So in this case, it's a loop, and what we want here, okay, I don't know. Anyway, let's go ahead and zoom up a little. We got a loop here. We have some changing magnetic field through it. Okay, and we want to find the current induced, it looks like. So if you come down to part B, we have a little trickier case where the magnetic field's a function of r, so a function of the distance from this axis out. Okay, and now find the current here. Alrighty, so if there's no objections, we're going to start with that. And if you have any questions, go ahead and ask them in the chat room. And right now I'm just pulling up the iPad display so we can work from that. All right, so let's go ahead and pull this up. And here we are. Okay, so let me just draw a quick picture here just to get an idea. So we got a circle. We got the z-axis up this way, the y-axis out here, z, y, and then x is coming out. So we just have x. And we have the magnetic field as a function of r from the origin. So B is equal to B0, 1 minus r over 2h. Sorry, that's messy. All right, let me go ahead and make this a little bigger. There we go. 1 minus r over 2h sine beta t ix. Okay. And we want to find the current that goes around this wire. And we're also told that it has a radius h. Radius h. It has a resistivity rho and a cross-sectional area a. Rho and cross-sectional area a. Okay. Let's go ahead and figure this out. Alrighty, so the law we want to use is what we want to, that's really what we want to start with. It's Faraday's law that says the flux through some area, the change in flux over time, is equivalent to E dot dr around the boundary containing the area. And so let's start off with this left-hand side since that seems to be the tricky part. First with the integral. And this integral shouldn't have a loop around it. We're just integrating over a flat two-dimensional area. This integral b dot ds. All right. So let's go ahead and plug in. Well, we're going to have ds. How do we want to orient ds first of all? Let's orient ds so it points out. This is what I call the Basquiat convention. And then that means we're going to integrate dr this way around the loop. He likes to use that in his book. All right, and if there are any problems with the audio or anything, let me know if I'm not being loud enough. Okay, so just check on the chat. All right, looks like we're doing all right. And we have more requests coming in. So yes, you can make requests in the chat room, or you can go ahead and chatting there, whatever. So we have ds pointing out. We have v in the ix direction, which is also out. Good. So this means that we're going to have the integral b0 1 minus r over 2h sine beta t here, and then ds, a nice perfect cross product there. All right. And so the idea is we want to integrate over the inside area of this loop. And so we want to break up ds so it accommodates this function in here, which is a function of r. And so the best way to do that, in my opinion, is to break this circle into rings. All right. So we have a constant b over rings of radius r. So here's the ring. It's got a radius of h. Okay. Here's the outside loop, rather. And I want to break it into a ring, okay, like this, which has a radius r. Wow, this is not a very good ring, but we'll deal with it. It's got a radius r, all right, and well, inner radius rather. And then the thickness is going to be just a little bit dr. Okay, so it's got a thickness of dr here and a radius of r. Okay, and so the area of that ring, or the area of that ring there, is going to be 2 pi times dr. I'm sorry, 2 pi r dr. Right, okay. So this ds here is going to be equal to the integral, and then instead of ds, we're going to have 2 pi r dr. Okay? And now we have all the stuff remaining in here. 1 minus r over 2h. Now, since we're integrating over r, we can go ahead and set the bounds pretty easily. We're going to integrate from r equal to 0 all the way up to the area of the ring, which is h, or sorry, the radius of the ring, which is h. And there we are. So let's go ahead and pull out all the constants, make the integral a little cleaner. Then we got a 2 pi, we got a b0, we got a sine beta t. Also, if you see a mistake or anything as we go, just let me know. All right, and we'll fix it. All right, integral from 0 to h, 1 minus r over 2h. Good. Alrighty. dr. Okay. So just to what we're doing is we're summing over rings with this much area, right? This is the area of this little this ring here, and what we're going to do is sum all those rings from r equal to 0 to a, all the way up to r equal to a. All right. So this first integral, so we just have these constants. I'm going to go ahead and just put some square brackets around it and just abbreviate. There's my constants. And my first term is going to be h in the integration. My second term is going to be r over 2 natural log. Oh, is that going to? No. We're integrating over r, Landon. Get with the program here. This is going to be r squared over 2. So r squared over 4h. We're evaluating it from 0 to h. There we go. Alright. And so we got the constants. We have h minus. And then this is going to evaluate to h squared over 4h, which is going to be h over 4. So 3h over 4 in the end there. So all these constants end up being 2 pi b0 sine beta t, if I didn't miss anything, which I very easily could have. And then we're just going to get 3h over 4 here. Does that look okay? Anything in the chat? Any complaints so far? What happened to 2 pi r? Shoot. Okay. Good question. It totally left the problem, and that totally changes the answer. Okay? So, good call. Let's pull out the constants here. We got 2 pi b0 sine beta t integral from 0 to h. And then we're going to have the first term be r minus r squared over 2h. Is that any better? I think that should do it. All right. Good? I think that's good. Okay, let me know in the chat if I miss anything else. Sorry about that. So 2 pi b0 sine beta t. Let's integrate this. And here we're going to get h squared over 2 for the first integral. For the second integral, we're going to get a 1 over 6h out in front, a minus sign out in front, and then we're going to get h cubed. There we go. So then we just got to add these fractions together. So we get this stuff, right, times h squared over 2, and then minus h squared over 6. So that's going to be 3h squared over 6 minus h squared over 6, which is equal to 2h squared over 6, or 1/3 h squared. And so we're going to get 2/3 pi v0 sine beta t h squared. I think I got that one right. Any complaints? Great. Thank you for the catch, Kevin. That was awesome. All right. So if there are no more complaints, I'm going to go ahead and integrate here. Hit this with a negative derivative with respect to time of b dot ds. There we go. So we hit this with a negative derivative, and we're going to get negative 2/3 pi b0, and now the derivative of sine beta t is going to be beta cosine beta t, so we get beta cosine beta t, and then we get our h squared here. Alrighty. Good. Now we got to do this integral, the integral of v dot dr around this loop. Alright, so let's go ahead and copy and paste this bad boy down there. And what we're going to do essentially is determine the direction of the induced current due to Lenz's law. Okay, we're going to see if we can reason our way through that. We'll pick a direction. If we get it wrong, we'll see our answer, and that's fine. Okay, so here we go. Alright, which way is the current going to be induced? Well, let's look at the magnetic field. Alright, and it's going to... Well, it's going to start off increasing because we have a sine function, and the original magnetic field looks like it's pointing out, so the flux is increasing initially due to a magnetic field pointing out. So nature wants to fight that by inducing a magnetic field pointing in. So using our little right-hand trick, we know that our magnetic field, let's go ahead and use another color, is going to be induced by a current going this way. So this is I induced. Okay. Alrighty there. So the integral of v dot dr around there, v dot dr. Alright, we doing alright? Okay, good. Is going to equal to, and we have a minus sign since we're going to integrate counterclockwise, and we're going to have our current going clockwise. So we have minus, and this has a resistance R, but it's written in terms of rho, L, and A. So let's break it down. We have negative IR here. This is negative I rho times the length of the wire, which is the circumference of the ring, 2 pi h over A, like that. Okay? I think that's all right. It's all there. So let's go ahead and set E dot dr integrated equal to this negative time derivative here, and we're going to get I rho 2 pi h over A is equal to 2/3 pi b0 beta cosine beta t, all times h squared. Excellent. So we've got an h on this side, we've got a pi on this side. Let's do some canceling. We can get rid of our pi's. We get rid of our 2's. We can get rid of our 1 factor of h here and an h squared here. And now we can write the current in all of its glory. I is equal to, looks like we have A B0 beta cosine beta t times h, all divided by, and it looks like we have 3 rho down here. Is that all right? And so it's a positive, so the direction of current that we picked up here is consistent with what we're getting from Faraday's law. I don't see any complaints in the chat. But by the way, let's go ahead and label what problem this was. This problem here was, what was it? It was a 2011 2B. So this was 2011 2B. Alrighty. 2011, problem 2, part B. We satisfied, Kevin? Let me know in the chat. You have any more questions on that? All right. So just to recap real quick, right? We use Faraday's law, here it is, to find the current induced around this ring due to this changing magnetic field. All right. So we needed to integrate B.ds, and so we need to think of a way to break up this ds to accommodate the function in here, where we have b essentially being constant over different values of r, but as r changes, we have different values of b. So we went ahead and broke this area up into rings of thickness dr and radius r. All right. Well, so the ds here, the area of a little thin ring, is going to be 2 pi r dr, and we integrate that function. Kevin's happy, so I'm happy. All right. Thank you. All right, and if you have any other questions on any other problems, let's go ahead and ask in the chat. But I have one question from guest 897. Why did ds change to 2 pi r dr? Wouldn't it be pi r squared dr because it's area? That's a good question. And it comes down to the fact that we're finding the area of a ring which is infinitely thin, right? Okay. So the idea is this. The idea is we have a ring. Okay. There we are. All right. And the circumference of it is 2 pi r, right? Now, if we just make it a little tiny bit thicker, all right, what's the area of this ring? Not the inside, but this little outside ring here. And that's what we're integrating over these rings, okay? And if dr is super, super small, you can just take the circumference 2 pi r and multiply by the thickness dr, okay? And that's the argument there. So okay, there we go. And that's why we said that's equal to ds, that little area of the ring. Good question, though. So that's for a guest 897. Anyone else have a question there? This is tricky stuff. But go ahead and take some thought, think about it there. All right, if there are no other questions, I got yet another request here. And let's see here. It is 2008 number 1. And then we also have question for 2013. Okay, so let's look at 2008 number 1 real quick. So this is 2008 number 1. All right. What I'm going to do is go ahead and pull it up on the screen here so we can all see what kind of beast we're dealing with. All right. So let me go ahead and first, what I'm doing right now is I'm just pulling it up on my screen, and I'm going to share it with you. So we have 2008 number 1, test 3 2008. Here we are, and there's number 1. Okay, so let me go ahead and pull it up on the screen for you real quick here, folks. 2008 problem 1. Okay, there we are. Here we are. All right. All right, great. So let's go ahead and look at the screen. Where is it? Blast. There we are. Okay. Look at the screen here. Let me zoom up a little. An infinitely long wire carrying a current I is a cross section of W. Cross-sectional radius of W. Okay. The current is uniformly spread over the cross-sectional area. If the center of the wire is at the origin, I have a really hard time seeing that. Even on my screen, it looks pretty bad. Okay, find the points on the x-axis where the magnetic field has 1/2 of the magnitude of the magnetic field at the surface of the wire. Okay. And so we want to find the magnetic field at the surface of the wire. Spoiler, it's going to be something like mu naught I over 2 pi times the radius of the wire, so mu naught I over 2 pi w. All right. So we want to find the value of x where we have half that amount. All right. And so this is a pretty nice problem here. I'm going to go ahead and pull up the iPad in a second here once I go ahead and pull up the question on this other screen. So we have, this is 2008 number 1. Okay, 2008 number 1. There we are. Perfect. Okay, so let me go ahead and pull up the iPad display. And I got my eye on the chat, so keep asking away there if you have any questions. There we go. Let's go ahead and pull up the iPad screen. La, 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 la. Sorry, Google Hangouts is not the fastest way of doing all this stuff, but it works. It records it when we're done. Alrighty. just like to take a brief moment to thank everyone who's joining in and participating so far. It's making this a lot more entertaining than it usually would be. All right. So here we go. So let me just draw that picture real quick. We have a circle, a wire, and here's a cross-sectional area of it. I is going into the page, all right? And it's going to have a radius of, I think, W. Yes, W. Alrighty. And so the x-axis is going to run over to the right. So let's draw our x-axis going this way, plus x. Alrighty. So find B, we'll call it B prime, so that B evaluated at x, the magnetic field evaluated at x, is equal to 1/2 of the magnetic field evaluated at x equal to W. All right. So this is what B prime is going to equal to. All right. There we go. So let's just find, let's just go ahead and write the expression of B of x, solve for B of W, and then make this relationship show up so we can solve for x. Now, I don't know if we're going to have time to solve for x, but whatever. All right. So what law or definition do we want to use? Well, for an infinite current carrying wire, right, we have this nice symmetry, which it talks about in the book, talked about in lecture, okay, so that we could pick Amperian loops, and let's pick the color blue because we like blue loops, right? Okay, so let me just get this blue real quick. Good. All right, and so let's go ahead and make a nice Amperian loop of radius r. All right. And we know the magnetic field is this nice symmetry due to this current, so that it has a constant value around the circle here, around any of these circles of radius r. Okay, it's a constant value, and it circles around that circle essentially. The magnetic field points tangentially to the surface of the circle all the way around. All right. So Ampere's law says that we can integrate around that loop. B, not knowing it, but knowing its symmetry, dot D, I think we use R here. If not, let me know. I'm pretty sure it's dr is equal to mu naught times the I enclosed, or the current going through this area that I made. Okay, so this is a cross-sectional view, so we really got current going into the page. How much of that current is going through that loop? Okay, so there's only a fraction of it in this loop. Alrighty here. So let's first look at r less than the radius W. Okay. So at the integral of b dot dr, around this loop we're going to get b, and we're going to integrate this way around. So we're going to integrate always this way around. Call this dr. It's going to go that way, and so we get b times 2 pi r there. For the right-hand side, we have that's equal to mu naught times I enclosed. Now, for r less than W, I enclosed is going to be a fraction of I, and it's going to be the sort of the ratio of areas here. So the area enclosed is pi r squared, and the total area of the wire is pi a squared. All right, pi w squared. Sorry. There we go. All right, and the idea here is to take the essentially area enclosed times the current per unit area. Okay, we know there's a total current I through the area of pi w squared, right? Go ahead and convince yourself of that if that's not true to you. And so to get the current enclosed by this little loop we made smaller than that area, we go ahead and take the area enclosed, which is pi r squared w, times the current I, so pi r squared w I here, divided by the total area, pi w squared. Okay. And so the magnetic field B is going to have a magnitude of mu naught I r squared over w squared, and then we're going to divide by 2 pi r, 1 over 2 pi r. Okay? And so for r less than w, we have B is equal to mu naught I r over 2 pi w squared. Okay, so we have a growing magnetic field. That's what that means. Is the function of r is r gets bigger, B increases. Now, for r bigger than W, okay, we're just going to have the situation where here's our current carrying wire of radius W, and now we have a ring bigger than W, okay? And so now I enclosed, sorry about that, I was sort of restricted by my little window here, but anyway, yeah, whatever. The I enclosed in any loop with a radius bigger than the wire is just going to be I. And so due to the same arguments, we're going to get B times 2 pi r is going to be just this time mu naught I, and then B is going to be equal to mu naught I over 2 pi r. All right. Now, if we're just looking at values along the x-axis, what I want to do is compare the value here. I want to find the value of x so that it's half of the value here that I've circled. So at some value x, it's going to have half that amount of magnetic field. All right. So what is it there? Well, it's equal to, so let's essentially write this expression here. Okay. So we want to find B. We want to find the value of x so that this is true. Okay. Let's go ahead and write that down here. I don't even know if the whole first part was necessary. The whole first half of what I did just seems like a huge waste of time now. Anyway, this is going to be mu naught I over 2 pi x. Because I do believe that, right, find the points, find the points x. Okay, so we're going to have two different probably possibilities here, right? We're going to have x less than a and x less than w and x greater than w. For x less than w, okay, here, this is going to be our magnetic field, okay, and we want to satisfy that condition that I just erased for some reason. Pretty sure I just had a, there we go, this condition, all right. So this is the condition, let's go ahead and move it down to a separate line so it doesn't look so confusing. This is the condition we want to satisfy, and in these two different regions, we're going to have two different expressions, right, because the B changes there. All right, so the left-hand side is B evaluated at x for r less than w, which is mu naught I x all divided by 2 pi w squared. That's equal to this evaluated at w, which is mu naught I over 2 pi w once you cancel out the w's. Okay, that's our first expression. So here we can easily solve for x. We cancel the 2 pi's, cancel the mu naught i's. It looks like here x over w, so we get a factor of w canceling here and here. X is, oh, I forgot the 1/2 here. The whole factor of 1/2 out in front. That needs to be, let's just sneak it over there. Okay. And so here we have x equal to 1/2 w. There we go. And now for x greater than w. Alrighty, we are going to have mu naught I. Here's the expression for x greater than w. Mu naught I over 2 pi x. 2 pi x is equal to 1/2 mu naught I over 2 pi w. And so we go ahead and we cancel everything out that's common. Mu naught i's, 2 pi's, 2 pi's. Okay? And now what do we get? We get 2w is equal to x. And there we go. This is for x less than w. And this is for x, sorry, this is for x greater than w down here, and this is for x less than w here. That's the sweet spot. Alrighty. I haven't checked the chat in a while. Anybody have any objections here? No objections? That makes sense to everybody? If not, just go ahead and ask any questions. But that should wrap it up for that one. Okay. While you guys are doing that, I'm going to go ahead and look up the next question that was requested, which is question 4, 2014, 2014, number 4. 2014. Oh, 2013. Okay. I didn't even read any of that right. It's actually 2013, number 4. Okay. Alrighty. It doesn't look like there are any questions on that last one. Okay. It's still not too late, so go ahead and get a question. And if you're confused, I'm going to go ahead and now bring this up on the computer in front of you in a second here. Let's go ahead and find it. So just a few things. Make sure to do a lot of practice problems the day before the test, and even the day of the test, just to sort of get it right in your head. Right in your head. Somebody asked, doesn't it also occur at the negative value of negative of 1/2 W and 2W? Absolutely, right? Absolutely. Since we have a, so let me go ahead and see. Let me go ahead and bring up the screen again. Okay, yeah, we're still on the iPad screen. Let me make it bigger. All right. So absolutely, we have the symmetry, right? The circular symmetry in this problem, and this is a very good point. Okay, so even for negative values of x over here, right? Negative x going this way, we're going to have the same value of x where we have this phenomenon, so that it's half of the value of magnetic field that it was at the radius. Okay, and so yeah, absolutely, this should truly should be plus or minus here, plus or minus here, and plus or minus here. So thank you, guest 398. That was very helpful. I appreciate that. Okay, and if there's anything else, let me know. I would have missed that. Thank you. Okay. Cool, cool, cool. So I'm going to start bringing up this next problem. It is 2013 number 4. 2013 number 4. Here we go. All right, let me go ahead and bring this up for you guys. 2013 number 4. Screen share. Our slow screen share problems. Oh, goodness. Okay, there we go. The slowness kills me too. It kills me. Okay. Awesome. All right. Oh, great. My favorite problem. I remember, oh, shoot. Oh, goodness. What is even going on the screen? I don't even know. Okay. Yeah, I remember when we graded this last year. It was just an absolute disaster. I don't know if anyone got it right entirely. Maybe like 1 or 2 people. But it's a really good problem. Basically, we got some rails, right? Some resistance-less rails, and this bar is going to slide down these resistance-less rails, all right? And it has a resistance R, and that's a nice, comfy problem. It's up at an angle theta, so it's sliding down an incline, sort of like 218 all over again. Now we do have one little hitch, and that's there's a capacitor at the bottom. See that? It's a capacitor of values with a capacitance C. So yeah, not the funnest time we've ever had in our lives, but we will get through it. And please, if there are any other questions, go ahead and leave them in the chat. And if you have any questions as we're doing this, bring it up in the chat. Looks like someone is now requesting 2010 number 4B, 2011 4B. I appreciate it. We'll see how much time we have. I don't want to make this video as long as the other ones, just because it's so dang boring, in my opinion, to put anybody through this. But if it's helpful for you, that's all that matters in the end. Okay. So let's take a look at this problem. Okay. There we go. It's up. Good. Let's make it bigger. Let's start drawing this out. Okay. So we got rails. Let me just take this off. We got rails. Rail. We got a capacitor at the bottom. Capacitor. Alrighty. This is up at an angle theta. Across the rail we have a bar. That it has a resistance R, and it's going to slide down. Alright, so let's color that in. There's a bar. Alrighty. Alright, R. This is a capacitance C. Alrighty. And this is the ground here, so we have a up at an angle like that. Okay, what else are we given? We're given that this distance here is W, so that's the distance between the rails. These rails are resistance-free, once again. And there's a magnetic field coming straight up, okay? And the magnetic field B is going to be equal to B0. Oh, that's super easy. We like magnetic fields that are that simple. All right. And then lastly, it gives you a nice coordinate system to work with. We have x equal to 0 here. And then going up the rail, we have the positive x going up this way. The end. Okay. So question A. Question A says find the equation that could be solved for the charge on the capacitor as a function of the velocity of the rod along the rails. Okay. We can do that. So we want to relate the charge on the capacitor plates to the velocity, all right? And there's only really one law that has any sort of relationship to a changing magnetic flux through some area, and that's what we have. Look, we have an area that's made of this bar, this end of the rail, and then these two rails here, right? And as this bar slides down, that area shrinks, and we have a changing magnetic flux through the area since it's getting less magnetic field. So this magnetic field B is uniform everywhere. It's sticking up everywhere. Okay. So this is the only law which captures those physics. So this is the only law we can use. B dot ds. Okay. That's what we want to solve. Alrighty. So which one do we want to do first? Well, I always like to start with the harder one. What's harder in my opinion is this. B dot ds. Let's integrate it. Okay, so first of all, notice that ds here points perpendicular to this area. And the angle between B and ds is the same angle that this incline comes off the floor. That's because, imagine that this weren't inclined. In other words, the circuit was sitting flat on the floor, right? Then the ds vector in B would be in the same direction. But as we slowly tilt the incline up to an angle theta, these vectors ds and b0 are also going to change by an angle theta, right? Because that ds is perpendicular to that area, which is climbing up an incline, all right? So we should notice that these two angles are the same and all that, all right? That makes sense? If not, just go ahead and say something about it in the chat. I'll go ahead and bring it up again, all right? So let's keep going here, all right? So the integral b dot ds, as we see, is b times ds times the angle between b and ds, or the cosine of the angle, rather. It's cosine of theta here, all right? Splendid. All right, so this is equal to b and cosine theta are the same throughout the area. We integrate over this area. It's just a rectangle, so let's call this x, all right? So the area is going to be w times x, so this side's just w, and then times x this way, w times x. Alrighty. Let's hit it with a negative time derivative. Sorry. Hit it with a negative time derivative, and what do we get? These are all constants in time except for x, so we get b cosine theta w, and x here, dx over dt. Remember this negative time derivative, so we need a minus sign here. dx dt is just the magnitude of our velocity, so we're going to write v, right? This is because v is equal to dx dt. We're hitting it, this whole expression, with the time derivative. All right. Next up, the integral of E dot dr around a loop. Oh, shoot, I need a drink. Okay. All right, I got it. I'm good. So now let's integrate E dot dr around this loop. All right. So let's figure out the direction the current's going to flow. We got a decreasing magnetic flux due to a magnetic field pointing up out of the area. Okay. So nature's going to want to induce a field reinforcing this. So B induced is going to be in this direction. All right. And to get a current flowing that way, we use our right-hand rule, and we see that the current must flow this way around the circuit, right? So that's a huge arrow there. That's a giant arrow. Something less dramatic would be something like this. Okay. I is going this way around the circuit. Okay. And so we have ds pointing perpendicular, pointing out, right? And using that same right-hand convention, we know that dr must go this way with the current, actually. So dr is going to go this way around the circuit with the current. In other words, we're integrating that way around the circuit. If we're integrating with the current, what do we get in the end? Well, we're going to get IR across the resistor, right? And now over this capacitor depends on which you call a positive plate, which you call a negative plate, so we must go ahead and label these plates. I'm going to say positive charge is going to pile up here since the current's flowing into it, and then it's leaving charges. It's the positive charges are leaving here, so this is going to be negative, all right? Now, the electric field points across these capacitor plates, points from positive to minus, so E dot dr, dr is in the same direction. We're going to get plus Q over C for that guy. Questions, please let me know if there are any. All right, and so let's go ahead and set this here equal to this here, okay? And I don't even remember what I'm solving for. I'm finding an equation that can be solved for the charge on the capacitor plates as a function of velocity. Okie dokie. All right. So what we end up with is IR plus Q over C, this is equal to that. Equal to negative B cosine theta, that's what Faraday's law says, right? WV. Lastly, we have two unknown functions of time. I of t and Q of t are both unknown, and we just want to solve for Q of t. All right? And so we need a relationship between the two. And we see that the current is a little bit of charge going down these wires. So this wire, let's follow it down, a little bit of charge dq, and that's all going to flow into this capacitor plate. So the rate at which this charge Q changes on the capacitor plate is the same rate at which the current's going through the wire, since it's charging it up, right? And so we can replace this I with dq over dt plus R. Oh, sorry, that's wrong. Times R plus Q over C is equal to negative B cosine theta WV. That's as far as we can go. So that's an equation that could be solved for Q. Now V is also an unknown function of time, right? So we can't solve this right away without knowing V, all right? So this is as far as we can go for now, all right? As far as the problem wants us to go. If there are any questions, go ahead and leave it there. Any more requests, leave them in the chat room. Looks like we got 2 more requests after this. I'll see if I can have enough time to just get to one. Okay, so let's press on here. The next question. Find the charge on the capacitor as a function of the velocity of the rod along the rails if the resistance is ignored. So, what does it mean to ignore resistance? It means set R equal to 0. So this equation tells us we have Q over C is equal to negative B cosine theta WV. I think that's it. And there's the charge as a function of velocity, right? We just got to multiply both sides by C, really. C? That's it. Cool. And notice here I'm getting a minus sign everywhere. And that's because V is less than 0, right? V is actually, right, dx over dt, and we see that x is decreasing over time based on our coordinate system, right? We go up to here. You see x is decreasing over time as this rail goes down, since x is equal to 0 at the bottom, and it increases this way. So this V is actually less than 0, making this overall quantity positive. So I did pick the right side for the charges. Part C. Okay, find the magnetic force on the rod in terms of Vx and Ax ignoring R. Magnetic force on the rod in terms of Vx, Ax. Oh my goodness, my life. Okay. Well, we know for a little segment of wire, ds, the amount of force on it is I ds crossed with the external field that it's in. Okay? I'm sick of scrolling up, scrolling down. It's no fun for anyone. So I'm going to go ahead and copy and paste this picture down here. And what I want you to focus on is focus on that wire part. I think we're still ignoring resistance. Yeah, we're still ignoring resistance in this part. It's a beautiful thing. So we have an expression for the charge on the capacitor plate as a function of time. And we know if we hit this with a time derivative, right, we know that we have the current, right? So let's start off by first finding the current through the wire. It's dq over dt. at least as a function of velocity. And that's equal to negative b cosine theta w dv over dt c. dv over dt c. Okay. And this is actually acceleration. Let's just write acceleration here. A. dv over dt is acceleration. Cool story. And that's equal to I. So we have ourselves the current in this formula. ds is going to be a vector pointing sort of not into the page, but across this rail. We can call it whatever we want. Let's just integrate. Let's call that the y direction, all right, or the z direction. Let's call it the y direction. Why not? Okay. So the total force on this little piece of wire, this green piece, is going to be the integral from y equal to, let's say, 0 to the length of that, which is w, and then I, which is given up here. I'm not going to put it in right now. There's no point till the end. And then ds cross b. So ds points, this is little s, not the same as d big S, which shows up in Faraday. Okay, that's just a little piece of length pointing in the direction of the current on a wire. And here's this green part's our wire. Okay, so ds is a little vector pointing in our positive y direction. B is pointing in the z direction. We'll call that z, going up. And so y cross z is x. So we're going to get a force in the x direction. Or rather, no, we're going to get a force not in the x direction, but in a direction which is this way. I'll go ahead and draw it this way. It's going to be all along this wire. Okay, that's going to be the force it's going to feel due to the current flowing. So here we have I, and then ds b, which is b0. And really all along here I could write a b0 everywhere since that's the magnitude of the magnetic field. I was just being sloppy. This should be b0 everywhere. b0, 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 b0. Okay, now let's go ahead and get back to the problem. So we take this, we integrate, and we get, and this is going to be in a direction, not in the x, but in this horizontal direction, sort of parallel to this slope. Not to the slope, but it's going to be in this this direction here. So let me go ahead and on this coordinate system, let me draw what I mean. So we have a direction going this way, right? We have a direction coming straight up, and then a direction going out, and it's going to be on this direction. Okay. Alrighty. So moving forward here. In other words, here's the best way to look at it. Okay, if this is the wire, let's say this is the green wire here. If the current's flowing into the page, let's say, okay, and B is going straight up here, B, and then I is going in, okay. And so you take ds cross B there, and you have a force which is going to the right. All right. So if I were to look straight down this wire, the force it's going to feel is to the right in this view. Okay, I guess that's sort of the home run way of looking at it. I don't think I could explain that any better there. Okay, anyway, moving on. So this is equal to I V0 W, and we can write this all like this. The force is going to be negative V0 squared. I'm just plugging an I down here. W squared cosine theta times the capacitance times the acceleration. All right, and it's going to be to the right. It's going to cheat. Alrighty. Now part D is bonus. Let's not even waste time. It's just using Newton's second law really to find the current through the rail. All right. So use Newton's second law. Let's just say part D. I'll just sketch it out how you do it. Use Newton 2. That's Newton's second law to find A. Here we have the force due to the current in terms of A, right? Alrighty, and then we can go ahead and plug A into this expression to find the current there. Okay, and that's sort of the sketch for how to do it. Okay, and then plug A into I. Part C, I think, answer. Or part, um, yeah, parts. It was not the answer in part C, but we used it in part C. I used in part C. Okay. Alrighty. I'm bored. I'm extremely bored. Let's not do that question again. All right. And what else do we got? We got more stuff. More stuff going on. All right. We have, according to the chat, we want to do 2010 number 4B. That's a differential for second order. Okay. Now, I heard a little spoiler from Tatiana, and there's not going to be any second order differential equations on the test. And that's not from Tatiana directly. I heard that from her students. Okay. So I don't think so. Let's look at this 2011 4B. How about that? All right. Let me go ahead and pull it up for you guys on here. Anything else in the chat? Nothing else is going on here. Anybody? Anyone alive? Okay. I don't know. All right. Let's go ahead and bring it up. Alrighty. So there we are. And we want to go down to 2011 number 4B. So here's 2011. Back to here. Alrighty. Okay. So it looks like in part A we have an RC circuit that's originally charged to Q0. Let me go ahead and zoom up. Okay, I lost my problem. Sorry guys. This is not cool. Where is it? Okay. Here we are. This is part A. We have an RC circuit that discharges. That's in your book. Not so interesting. Okay, and in part B, in the circuit below, we have a capacitor. This is going to be my last one. Let's not make this too terribly long. And then I'll answer any general questions at the end. Okay. So let me go ahead and type that in, ending with 2011 4B. Then general questions. All right. I typed that in the chat. Okay, so let's look at this. Capacitor C2, capacitor C1. C2 is initially uncharged. C1 is charged to Q0. At T equal to 0, the switch is closed. Find the charges on the capacitors as a function of time, assuming the self-inductance of the circuit is to be ignored. Okay, so ignoring self-inductance is good when you're supposed to. And in this problem, you certainly are supposed to because it tells you to, right? If it doesn't tell you to, don't ignore it. Okay. And so let me go ahead and bring this up on my other screens. 2011 number 4B. Okay. Just going to bring it up on my other screen so I can see it while I'm explaining it to you guys. And now I'm going to go ahead and bring it up on your screen here. Let's get to Google Hangouts and let's get it up for you. Okay. And so here we have two capacitor plates, and this anytime you have two capacitor plates, something like this, a conservation of charge is usually going to pop into the problem somewhere. Okay. So let's not forget that's going to come into play at some point. All right. So let me go ahead and get it here. Draw the problem. Alrighty. All right. So this is 2011, exam 3, of course, and this is going to be 4B. All right. So what do we got? We got this circuit. We have a resistor. We have another capacitor here. So this is C2. And then it hooks up to C1 like that. Okay, C1. Alrighty. This has a resistance R. C1 initially uncharged. Okay. C2 has C2 is initially uncharged. C1 has an initial charge of Q0. Okay, so we'll call it Q1 initial is equal to Q0. All right, and then Q2 initial is equal to 0. Q2 initial is equal to 0. All right. Ignore self-inductance. Now find the charge as a function of time on both the plates. Okay. Inductance. All right. If we didn't ignore self-inductance, we would have an LRC circuit. A little complicated for right now. All right. What's the only law we know to use? And that's Faraday for circuit. And then inductance. Unfortunately, I didn't get any problems where I really got to talk about this, but remember we have this plus or minus Li that comes in here. Positive if the flux is positive, negative if the flux is negative. That all depends on the direction of ds, right? If you pick ds to be one way, it could be positive. Ds to be the other way, it could be negative. But that minus sign difference will always be recovered when you pick dr. Well, you get dr from ds, right? Anyway, basically, in this problem, we're ignoring self-inductance. That's what it tells us to do, so this is 0. And we just have our typical case from before. Not very typical in real life, though, of this. Okay. And let me go ahead and make the screen a little bigger for you guys. All right. So let's close the switch here. Close the switch. Just put it in another color, orange. Okay, and then now we're going to find the integral v dot dr around here. Before we can really achieve that, we gotta go ahead and label some charges. So let's put a positive Q1 here and negative Q1 here. And I'm gonna say positive is gonna flow to a oh geez, I don't even know. Let's say we're gonna get more positive charges Q2 here, right? So your answer will depend on how you label it. So you gotta look at the labeling. So if my answer is different from the answer key by like a sign, then it's because of my labeling is different from theirs, and that's okay. You can do that if you'd like. Okay. Actually, no. Let's flip it around. I mean, I don't know, just for fun. Let's see what happens. Negative Q2 here and Q2 there. See, I can do it whatever way I want. Just make a label and stick with it. Okay. Anyway, integrate around the circuit. So I'm gonna guess that the current there is gonna be some current, right? When we close this switch, it's going to flow from here to here, right? So let's go ahead and label that with an arrow here that says I. And that same current will be down there. All right. And what else do we need? Well, let's use the baskets convention of pointing ds out and integrating around this way. In other words, that's the direction of dr in my path integration. Okay. And so we integrate around this way, so let's start here. All right, start at the top plate. We're integrating with the electric field, so we're going to get a Q1 over C, Q1 over C1. And then we continue down here, and we go across here. All right. And once again, we're going with the electric field, so we're going to get Q2 over C2. Once again, this sign is this plus sign here. It could be a minus if I just switch my labels, right? Hope you understand that. Please take some time to convince yourself of that's true. If not, if that's not obvious to you right now. Okay, and then minus IR is going to be across here, and then that's it. That's equal to 0. Okay, so you have 3 unknown functions. Okay, 3 unknown functions. That's the worst spelling of unknown I've ever seen in my life. Okay, functions. That's a little closer, probably. All right, we have I of t, unknown. We have Q1 of t, unknown. Q2 of t, unknown. We have one equation. Okay, just one. So we need some help. All right, and the help comes from this conservation of charge idea. So we see this, well, that's one place where the help comes from. Okay. Okay. Anyway, so we go ahead and we see that this strip of wire down here is isolated, which means the charge on it. I can't get it all into one box, but you see this strip of wire that I'm highlighting. Okay. Well, that, including the little plate on the top left side, that little bottom negative Q1, that is going to be isolated from the rest of the circuit. So the charge on it must be constant over time. In other words, what I'm trying to say is initially, what's the charge on this bottom strip of the circuit? Okay, and that initial charge was given to us in the problem. We said that Q1 has an initial charge of Q0, okay, and Q2 is initially uncharged, right? So initially, so this is conservation of charge on that bottom strip. We have negative Q0 since we have the minus plate down here, right? Plus 0 must be equal to negative Q1 plus Q2. Oh, wow. Great. Okay. So let's go ahead and see what this means. So that's the relationship between Q1 and Q2. So I could find Q1 and get Q2 from this relationship, right? We're just simplifying it. We're going to get Q2 is equal to Q1 minus Q0. Right. Based upon now once again, this relationship is going to be different depending on how you label your charges. Anyway, let's not. I'm really slowing down here. Let's just keep going here. All right. So this current I is the next order of business. All right. So now we have a relationship between the two charges. What's this current I? So we have this current I here, which is coming out of this capacitor plate. So the rate at which Q1 changes, it's going to decrease, right? That's going to cause an increase in this current here, right? And so the relationship is we have I being negative dQ1 over dt for the discharging case. All right. All right. So let's go ahead and write this whole expression up here in terms of Q1. All right. So we're going to need Q1 over C1 to start with. Plus, and then Q2 is Q1 minus Q0. So we get Q1 minus Q0 divided by C2. Alrighty. Minus, and then we have a negative dQ dt, so plus dQ1 dt is equal to 0. Okay. Now we got to actually find these charges as a function of time. Okay. And so let's write this in what I like to be, what I call a more standard form. All right, let's get all the Q1 functions. First, let's get dQ1 dt by itself. Where's R? What happened to R? R should be here, right? Okay. So let's divide by R to both sides. So we get dQ1 over dt, right? Then let me write so 1 over R here. Then all the Q1 functions by themselves. Well, Q1, all the Q1 functions by themselves, so let me factor it out. We're going to have 1 over C1 here, and then 1 over C2 here. And on the right-hand side, I'm going to put anything that does not involve Q1, where the only term that is this negative Q0 over C2 term. I'm moving it to the right-hand side, and remember that I divided by R, so I get Q0 over RC2. So if going from this step to this step is just totally mystifying you right now, please take some time to convince yourself that's true. And if I did make any mistakes, let me know. But that should be right. Okay. Q0, let me just double check. Yes, I do believe that's right. Okay. Anyway, let's move forward. Okay. And so the way to solve this equation is to say Q1 is composed of two parts, the solution, a constant part and a homogeneous part. The constant part satisfies the fact that dQ C over dt is 0. In other words, it's constant in time. Plugging this into, this is the equation we're working off of, all right? Plugging this into the double star equation gives us the first term is 0, since that is 0 by definition. We get 1 over R, 1 on C1 plus 1 on C2. And then we get QC is equal to Q0 divided by RC2. And this tells us that QC is equal to, and the 1 on R is cancel on each side. And the best way to write this is Q0 over C2. And then write this fraction like this, 1 on C1 plus 1 on C2 to the negative first power like that. Okay. Okay, carrying on. Now, this second part, this homogeneous solution, satisfies the following equation, okay? And the way you get it is just by setting the right-hand side of this equation equal to 0, okay? And so this equation must satisfy dqh over dt plus 1 over r, 1 on C1, 1 on C2, QH is equal to 0, all right? And so when we see an equation of this form, we guess QH is equal to A e to the minus BT, unknowns A and B. So we need to plug our guess into this satisfying equation called the homogeneous equation, okay? So we need to take a derivative of QH with respect to time. That's minus BA e to the minus BT, which is equal to, and don't be a stranger to this, all right? I can write it like this. It's no big deal, right? Because QH is just going to be A e to the minus BT, so I'm just replacing this with QH. It's no big deal, right? Now I'm going to go ahead and plug this derivative into here, solve for Q, and see what that says. So we get minus BQH plus 1 over R, and then 1 over C1 plus 1 over C2 QH is equal to 0. And therefore, from this equation, we see that if I say go ahead and separate the QH term, so I factor out the QH term, that can't be 0, right? And so what's left is minus B plus 1 over R, and then 1 over C1 plus 1 over C2. And then that's it. So what we see here is that this must be equal to 0. This QH can't be 0. So what's in the parentheses must be 0. Okay. And this tells me that B must be equal to what's to the right of it for these to add up to give me 0. So B must be equal to 1 over R plus 1 over C1 plus 1 over C2. Okay. Alrighty. Goody, goody, goody. All right. So that's my unknown parameter B in this guess. Now, total Q, right? That's equal to the homogeneous solution plus the constant solution. I just wrote it in the reverse order that I'm going to record it. So we take our constant solution, which is equal to this. All right. So here, there it is. And then we go ahead and write that here. And then we go ahead and we add that to our homogeneous solution, which is A e to the minus BT, where B is equal to this. So plus A e to the minus BT minus 1 over R, and then 1 over C1 plus 1 over C2 T. C1, 1 over C2 T. Okay. Awesome. And this is Q1 rather. Q1. Okay. Now use the initial value of Q1 to get A. So the initial value of Q1, let's go all the way back up to where we wrote it. Holy smokes, long problem. It's Q0, okay? And we are definitely ending with this problem. All right. So if you have any general questions, just go ahead and get them in the chat room right now, or any questions on this problem. Q0, okay? So what we do is we take this condition, we set the right-hand side equal to, or the left-hand side equal to Q0, and at the same time evaluate it at t equal to 0 here, making this exponential a 1. And so we get Q0 is equal to Q0 over C2 plus 1 over C1 plus 1 over C2. Sorry, this should be, yeah, that's right, to the minus 1. Plus A. Okay. So A is then equal to this complicated thing. A is equal to Q0 minus, I can factor out, it doesn't really matter at this point, Q0, how do I want to write this? 1 minus 1 over C2, okay, 1 minus 1 over C2 times 1 over C1 plus 1 over C2. You could simplify this and see what it ends up being if you want, but either way, this is how you do it. Okay, I just factored out a Q0, right? I have a 1 due to this term, and then minus this stuff. And therefore, this is Q1, right? So Q1 is this here, and here's the value of A that we need. Okay. And what else? Now we need Q2. So what's the condition? Q2 is equal to what? Now we had that relationship written above. It's Q1 minus Q0. Okay. Q2 is equal to Q1 minus Q0. So we just take our solution here, we subtract off Q0, and that's Q2. I'm just going to circle it and say it's good enough, since we know in principle how to get it. Okay. Now, you could use the fact that 1 over C1 plus 1 over C2 is equal to C1 plus C2 divided by C1 times C2, right? So that 1 over C1 plus 1 over C2 to the negative first power is equal to C1 times C2 divided by C1 plus C2. And you can use this expression to simplify this, and it'll end up being just C1 over C1 plus C2, all right, here. And so you can use that expression here and here, and, well, not really here so much, but more so here, here, and I'll simplify things a bit. But other than that, there's not much other place to go. I'm going to go ahead and check the chat here and see if there are any general questions. If you got any questions you want to ask me before we log off here, this is a good time. Just going to remind you, do a few problems today, do a few problems tomorrow, a few problems before the exam just to get you warmed up. Do not wear yourselves out before the exam too much. Get a good night's sleep. That's one of the most important parts. Physics is not so much what you memorize, but sort of your mental state while you're taking the exam, as you know, right? So you can study and study and study, and if you're too tired to do anything, it's not going to make a difference on your score. All right. Okay. So we'll give about 1 minute here to wrap up. Thank you guys for participating once again, everyone in the chat room. Let's see here. Guest 398, thanks. 897, thank you. Kevin for the win, thanks for the initial question and for the catching my mistake. 897, thanks for the questions. We have a question here from the chat room from guest 398. How to know when to use Biot-Savart and Ampere's law. So Biot-Savart's law you use when you have essentially an infinite wire or some sort of symmetry where B is constant around some loop you can draw. Now these don't have to be circular loops, right? You can also draw rectangular loops, and B can be constant around those. The examples for that would be an infinite sheet of wire and a solenoid. So you can look up in your book, you know, the magnetic field in a solenoid, and there you have a rectangular loop, and you use Ampere's law to go ahead and integrate around that. And then an infinite wire, of course, you have this nice circular symmetry where you can circle around the wires, and you have B is constant at a constant radius around the wire, and so that allows you to integrate B dot dr easily over a circle that surrounds the wire, right? It's centered at the same point that the wire is centered. And then when you use Biot-Savart, that's also known as Ampere's principle in the text. This dB is equal to mu naught I over 4 pi ds cross r over r cubed. So no one asked a Biot-Savart question or an Ampere's principle question, and that's really just setting up the integral. So if you look at 2013 number 2, you have the infinite wires, the semi-infinite wires. They're sort of bent. And then also I did a video where I used Ampere's law, or sorry, Ampere's principle / Biot-Savart's law to calculate the magnetic field at a bent infinite loop with a circular bend in it. So you can look that video up, but that's the difference. That's how you know when to use the two. In other words, Biot-Savart or Ampere's principle, you're not going to have some nice symmetry where B is constant around some loop. Okay. And sometimes you do have a nice symmetry where B is constant around a loop. It just ends up that B is 0 around that loop. So that doesn't really help you calculate the magnetic field at anywhere, really. another good example of Biot-Savart or Ampere's principle is in your book. It's in the chapter at the end of that chapter, that Ampere's principle chapter, and it's a square loop of current. Take a look at that for more practice. But there will be at least one question where you use Biot-Savart or the Ampere's principle, and there will be at least one question where you use Ampere's law. Okay, so know the difference between the two, know how to apply to, and it'll be a 25-point difference if you don't know both of them. So make sure you do know both. All right, nothing else in the chat. Thanks, guys. I'm glad it was. I hope it was helpful, and I'll see you guys at the exam later.